And it's my pleasure to introduce Dr. John Walsh. John is a President's Professor of Global Climate Change at the University of Alaska Fairbanks, and he's also the Chief Scientist of the International Arctic Research Center in Fairbanks. His primary research interests are Arctic climate change over the decade to century timescale, predictability of climate change in high latitudes, and he's also done a lot of work on extreme events and the role of climate change in changing the frequency of those events. So with no further ado, I will introduce John and let him take it over from there.
Thanks. Okay. Thanks, Marika, and thanks to everyone for coming back from lunch. Having a thinner audience right after lunch is almost a given. It does let one go farther out on a limb in what they cover in the presentation. So we'll see how it goes. The theme 3 does address Arctic global linkages. So it expands the range of the Arctic's impacts. And I'll try to highlight some of those expanded impacts in what I go through. And my strategy will be to highlight several linkages between the Arctic and the global system. And these are linkages that have really come to the fore since the last State of the Arctic meeting back in 2003. So I'll step through them in the 20 minutes or so, and I'll go through 5 of them. And in going through them, there are several questions I'll at least touch on. What have we learned recently about each linkage? Why does the linkage bear watching over the next few decades? And what should we be watching? And I should add that some of these linkages do have uncertainties, and there are debates about processes at work. But I think the debatability aspect is one reason why we're here for this conference. So I'll start out with the first linkage, which is posed as a question. Are changes in the Arctic impacting mid-latitude weather and climate? And I'll try to build the argument here around the past winter. This past winter of 2009-10 had record snowfall over parts of the US, extreme cold and storms in Europe. It was certainly not a typical winter. Can we make a linkage between the Arctic and this winter, and this particular winter's weather in mid-latitudes? So I'll come back to the linkage after we step through what has been going on in the Arctic over the last few years. This figures a time series of the annual Arctic temperatures. It's from Pasha Groisman at the National Climate Data Center, and it's been shown, similar versions have been shown a couple times. And the point I wanted to make here is that the last 4 full years of data, which are represented by the filled-in circles there, are the warmest years in the entire record in the Arctic. This record goes back to 1880. There's a provisional value in there for 2009. But the point of this is that in spite of all we've heard about the pause in global warming, the pause in the warming globally, there has not been a pause in the Arctic. In fact, the last few years have been the warmest, at least on this centennial time scale that we can point to. If we look at the spatial pattern, we find the classic polar amplification. In fact, the warming, and this is highlighting the anomalies of the last 5 years relative to the previous half century. There's an amplification with a maximum over the sea ice zone, and that's going to point us to the start of this linkage that we'll be talking about. And if one wants to zero in on the sea ice impact even more, one can view the warming in a latitude versus season time frame. So the Arctic is up here at the top. As we step through the year, this warming has been greatest in the autumn and winter, especially the early winter. That's precisely when we would expect sea ice to be impacting the atmosphere. There's even a secondary peak out in here in the spring, which could be tied into an earlier melt. But the fall and the winter are the seasons when the signal stands out. There is some interesting work taking this a step further. It was done by Jim Overland and Muyin Wang. It's in a paper in TELUS recently, showing how this warming in the high latitudes in autumn translates to changes in atmospheric pressure and winds. And that's going to start getting us towards our link to mid-latitudes. In a nutshell, the warming does cause a sort of a thermal expansion which raises the pressures aloft over the polar region. Increasing the pressure aloft will reduce the westerly winds, and that means it's going to reduce this annular mode, this pattern of westerly winds that's a dominant mode of variability. So we'll come back to that one as well. But let's take a particular look at this most recent winter now and how that plays into this more general pattern that we've been seeing. These are the temperature anomalies for the past winter, December through February. And the Arctic was extremely warm this past winter. The cold weather, the cold low temperatures in mid-latitudes show up, but the Arctic was 4 to 6 degrees C above normal. So it's certainly fitting that pattern that produced the anomalous winds that Jim Overland and Nguyen mentioned. If we look at the sea level pressure anomalies this past winter, we have a classic example of a weakened Arctic oscillation. Higher pressures in the North Pole region, lower pressures in the mid-latitudes, especially in the oceans. This is classic Arctic oscillation anomaly pattern in the negative mode. So what we're saying here is that the winds are weakened over the subpolar North Atlantic and the North Pacific. So this past winter conformed to what we've seen over the past 5 to 10 years, according to Jim's work. The outstanding feature in this linkage between the Arctic and mid-latitudes is now this weakened Arctic oscillation, the pattern on the right in the upper pair there. Down at the bottom is a graph of the Arctic Oscillation Index over the last several months. This goes back to November through just a few days ago. And these extremely negative values show up. The scale here is standard deviations. This Arctic oscillation was 3 and 4 standard deviations below its mean, which is, in this case, literally off the chart, off the scale. So the bottom line on this first linkage has to do with what went on last winter. The preliminary evaluation or diagnosis of the past winter's anomalous weather has been gone through by the NOAA Climate Diagnostics Group with Marty Hurling. And they've pointed out that the two factors contributing to the severity of the winter in at least the US and Western Europe were the occurrence of an El Nino in the Pacific and the extreme negative phase of the Arctic oscillation. This El Nino provided the storms, the storm track. The Arctic oscillation provided the cold air that made the impact or the precipitation snow instead of rain. So those are the two large-scale features. The Arctic, we're arguing, is a factor here in the Arctic oscillation. So we have this occurrence now of sea ice loss over the past few decades, winter warmth in the central Arctic, and an extreme negative Arctic oscillation. So we can ask the question, is that just a coincidence? And the answer is, perhaps it is just a coincidence. And it's perhaps even probably just a coincidence. But I would contend that this does bear watching as sea ice retreat continues, and there is the potential for the impact on mid-latitude weather during the winter season. So that's one of these linkages. The second one was touched on by Dr. Bement yesterday. It's this recent information on methane releases from the Arctic Ocean. And I have a quote here from a paper that appeared a couple of weeks ago in Science magazine, the Shakova et al. Paper, pointing out that this release of methane from the Siberian shelf region offshore of the northern Russian coast may trigger abrupt global climate warming, which certainly would be a global impact. And they point out that the current venting flux is on a par with estimates of methane venting from the entire rest of the world ocean. And this was summarized nicely in a schematic that NSF produced in a press release on this research. The point they make here is that there's a permafrost layer below the surface in the Siberian shelf region, and that's perforated, and that's enabling some of the methane to reach the atmosphere. The study itself points to regions of enhanced methane concentrations in the ocean. These are generally above the higher bottom topography areas, and this venting from the perforations in the permafrost layer, it shows up in the transects, the measurements that were made on the icebreaker that was used. Now, the key question in this particular work is, how do these releases fit into the big picture? This is a figure from Dave McGuire, who showed it in his talk yesterday, summarizing the carbon stocks and some of the main fluxes of carbon in the Arctic system. And the point here is there are large other stocks of carbon and methane in particular on the terrestrial part of the system and in the deeper ocean. And the final summary on this particular linkage between the Arctic and the rest of the globe is this statement that accompanied the science article on the methane release. This was a perspective article. And I've actually quoted Hyman here in the summary of the findings. The methane releases from this Siberian shelf region were estimated in the paper to be about 8 teragrams of carbon per year. Global emissions are about 440. So the conclusion here was that these emissions that were described in the paper are probably negligible in the big picture right now. But the key point is highlighted in red. The question is, will that conclusion persist into the future? And the answer was a resounding, we do not know. So once again, we have a process here in the Arctic that bears watching with potential global implications. The third linkage is one that gets quite a bit of attention in the Arctic global context. It's the contribution of Greenland and Arctic glaciers to sea level. So we want to at least try to provide an assessment of where things now stand in this linkage. Since the 2003 meeting, there was a fairly comprehensive study by the Colorado group, Mark Meyer's group, estimating the contributions to sea level rise from glaciers and ice caps, Greenland, and Antarctica. And they partitioned these 3 sources into their volume and area, but the red is the important part here. That's the percent contribution to sea level rise from these different cryospheric components as of the early 2000s, the early part of this decade. And the main conclusion here was that the smaller glaciers and ice caps were actually making the larger contribution to sea level rise as of 5 or 10 years ago. Since then, there's been a lot of work and a lot of attention given to Greenland. And just in the last 5 years, the mass balance of Greenland has gone quite negative. The discharge of water into the North Atlantic has increased fairly dramatically. And the revised estimate of the mass loss from Greenland is now up to about 270 gigatons per year, which is equivalent to about 3/4 of a millimeter per year, which is actually comparable to that estimate from the smaller glaciers and ice caps. So we now have 2 cryospheric sources of 2 contributions from the Arctic to sea level rise, totaling about 1.5 millimeters a year, and that's on the order of 50% or even more of the total sea level rise. So right now we have a connection between the Arctic and the rest of the global system through sea level rise. Number 4 is the relationship between the inflows to the Arctic Ocean from the Atlantic and Pacific and changes in the Arctic. And we've seen in many talks at this conference the retreat of sea ice. This figure on the right that we'll come back to is the ice cover at last summer's minimum, 2009. The one on the left is the 1980 minimum. The point here is that we have warmer water entering the Arctic from the Atlantic, subducting to middle levels. We have water entering through the Bering Strait, remaining somewhat closer to the surface. We also have runoff. So the real question is, what are changes in these inflows of Pacific and Atlantic water contributing to the changes we're seeing in Arctic sea ice? This is a figure from Igor Polyakov summarizing the results of 8 years of cruises along the Siberian shelf break during the summer. They've color-coded in the temperatures measured along several transects. And this is a striking example of low-frequency variability. The purple color represents the warmer water. So in the early part of this decade, you can see a warming at all the transects. Igor has done some calculations to show that at least some of this heat is likely reaching the base of the sea ice and contributing to melt along the Siberian, seas offshore of the Russian coast. What's interesting is that in the last, well, down here at the bottom, the last couple of years, there seems to be a reversion here of a reversal of the warming. We've actually detected a cooling in the last couple of years. And if one looks at the sea ice distribution, there was actually more ice in this region in the past summer than there was 2 summers ago. So there does seem to be some consistency between what's happening with the ice and what's happening with the properties of the Atlantic water that are influxing to the Arctic. The other point here is the Pacific side. If one looks at this sea ice distribution last September, that pattern almost has Pacific water influence written over it. I mean, there's this huge gap in the ice cover north of the Bering Strait. Some work has been done by the Japanese, Koji Shimada, arguing for a feedback loop between ice concentrations and warming of the waters offshore of the Alaskan coast and the Chukchi and Beaufort Sea region. And he's shown how this warming coincides with a decrease of ice cover. Now, this is one where there's some debate. I mean, the role of the Pacific water inflow in initiating this feedback loop isn't clear. It could be that some wind events, some unusual wind forcing over a couple of years triggered this feedback loop. But it does appear that the Pacific water inflow is one candidate for what we're seeing in terms of ice retreat in this area, and it's probably involved in one way or another with the changes we're seeing. To wrap up this topic, there are a number of factors that seem to be contributing to the sea ice retreat, and I've highlighted in red this preconditioning by the Atlantic and Pacific water inflows. And I think that the challenge we face is to place that into a quantitative framework that also includes the effect of the variable wind forcing and the feedbacks that go with the loss of heat and the reduction of with the reduced albedo and the storage of heat within the ice. But in any event, the inflows are probably at least part of the story here, which reinforces this Arctic global connection. The last of the 5 linkages is one that involves the freshening of the North Atlantic and subpolar seas. And I think the big picture question is whether this has an effect or may have an effect on the global ocean conveyor. This is a figure from a paper by Curry and Moritzen a few years ago. It's pointing out that this region here is the action zone as far as the driving of deep convection, at least in the North Atlantic, goes. And what they showed was that there has been a freshening in terms of a reduction of salinity and density in the region north of the Denmark Strait sill, the overflow region. So this freshening does show up in the Iceland Sea. It's less apparent south of the Denmark Strait sill because the tropical waters can influence this region. But it's this freshening here. It's actually been looked at in a little more detail by Bruce Peterson's group. That group tried to track the freshwater storage in this North Atlantic subpolar seas region. And what they found was that there are a number of contributors to the freshening. The precipitation minus evapotranspiration was a significant contributor. Sea ice attrition, the loss of sea ice, was another contributor that actually built up this freshwater storage over the past several decades. And this study really didn't include the inputs from Greenland, certainly not the last 5 to 10 years worth of additional input from Greenland, which could easily raise the freshwater anomaly in that region. But I think the picture that's emerging here is one that's producing a consistency between what we're seeing in the ocean data, the lower salinities, and what we're seeing in the atmospheric and the sea ice data. So all signs point to a contribution from the Arctic. And this is a last slide on the freshening. The summary statement's up at the top there. This is from the Curry and Maritson paper, pointing out that at the time their study was done, about 5 years ago, the observed rate of freshening would require about a century to affect the overflows substantially. Now, the caveat on this is that Greenland was really not factored in. So I think we do have more work to do in putting together the changes just of the last 5 years. But I think the target on the horizon here is this thermohaline circulation and what may happen. I think this figure was shown in one of the earlier talks. It's a summary of the model simulations of the thermohaline circulation intensity. These are the IPCC AR4 simulations. And the point here is that none of the models project a strengthening of the meridional overturning circulation in this century. Quite a few of them predict a weakening, some a fairly drastic weakening. So given that we are seeing more freshwater input into the North Atlantic, a freshening of the surface layers of the North Atlantic, this is another one that probably does bear watching. So here's the summary. 5 items we just went through, 5 Arctic global connections. The point I wanted to make is that 4 of the 5 really have the Arctic contributing to or even driving global changes. This 4th one is one where the mid-latitude oceans are really providing the influxes to the Arctic. But I think we have quite a bit of ammunition here if we do want to point to ongoing and certainly potentially important influences of the Arctic on the global scale. So I'll stop with that and say thanks for the attention.